Hello, everybody. I'm Dr. Franklin, Assistant Professor at Norfolk State University, and I am doing this broadcast as a way in which to talk about the normal curve and how it relates to the z-score. Okay. So let me go ahead and draw out this normal curve. And go ahead and draw the lines within the normal curve. Okay, and I'm going to draw some symbols and numerics underneath it that are associated with our usage of the normal curve. 3. Let's put that up at the top. And in the middle is going to be our mean, median, and our mode. -1 standard deviation, -2 standard deviation, -3 standard deviation. Okay, and there's certain percentages that are going to go in here. Okay, so this is the normal curve, okay, also known as the bell-shaped curve. So normal curve, bell-shaped curve, and it represents a normal distribution. In other words, it represents a usual data set and how scores will distribute around the mean, the median, and the mode, okay? It's symmetrical. And the whole distribution equates to 100%, okay? So you've noticed at these different inflection points, there's percentages that are associated with the spaces. So going from the mean to 1 standard deviation, we have 34.13%. Then going from 1 standard deviation to 2 standard deviations, there's 13.59%, and then so on and so forth. So 1/2 of the distribution equates to 50% of the data set, and the other half of the distribution equates to 50% of the data set. And these percentages are fixed, okay? So these are never going to change. These are pretty much fixed if you're dealing with a normal distribution that doesn't have a lot of peaks, that isn't a bimodal distribution, and that doesn't have a lot of extreme scores. This is how it will distribute. So for the most part, you see that the bulk of the scores are towards the middle, or are clustering around this mean, or they're clustering around the sample mean. Okay. So I said that these percentages are fixed, so these are never going to change. So you can go ahead and lock those into memory. However, what these standard deviation units actually equate to will change based on your data set. What this mean, median, and mode equates to will change based on your data set. Okay. Just to recap, it's a normal curve. It's a bell-shaped curve. It represents a normal distribution or typical data sets out there. So with your final exam grades, I'm expecting that it's going to assume a normal distribution with the bulk of scores being around the average of the class. Okay. It's symmetrical, so if I was to fold the sheet of paper over, both of these sides would equate to each other, and it takes into consideration the entire distribution. Okay. So how this relates to z-scores is this way. When we transform a raw score into a z-score is nothing but a standard deviation. Okay, so if we recap, the formula for a z-score, we'll find that it's x minus whatever the sample mean is over s, and that's for a sample, or for a population, our formula will look like this. Be x minus mu, that u, over a population standard deviation. Okay. So essentially what we're doing is we're getting the position of a particular raw score as it relates to a sample mean and how spread out that data set is. Okay, so this is incorporating some of the stuff that we've talked about before, that measure of central tendency as well as the measure of variance. And we know that whatever you divide something by, you will essentially transform that number that's being divided into that. Okay, so we can take a raw score, transform it into a standard deviation unit, and then upon doing that, we can apply it to this normal curve, and we can determine how well a particular score fares in light of that particular data set's mean, in light of that particular data set's standard deviation, and how spread out the scores are. Okay. So let's just do a little quick example so that you can see what I'm talking about, and I'll scoot the paper down just a little bit. So let's say we had the raw scores of 2, 4, 6, 8. Okay, and we wanted to know where the score 4 fell in terms of this data set's mean, and in terms of how much variation is within this data set. Okay, so because we're using so few numbers, you may be able to use deductive reasoning and figure out that, for the most part, this 4 would probably be below the mean. However, to get a little bit more specific, and when we're using larger data sets, it will be necessary for us to actually go through and calculate means and calculate standard deviations so we can get an understanding of exactly where this 4 falls in terms of the mean and in terms of the standard deviation. Okay, so let's run through a problem really quickly. If we wanted to, from scratch, just using raw scores, and n equals 4, right? Let's assume this is a sample. So we'll be using this formula. Let's kind of run from scratch what we would have to do in order to find out how 4 is doing relative to all these other scores in regards to the central tendency and standard deviation as well. So you can look at my other video to track how to calculate a standard deviation. I'm just going to run through the steps rather quickly. Step 1 is just calculating the mean. So 2 plus 4 plus 6 plus 8. So we have 2 plus 4, 6. 6 plus 6 is 12. 12 plus 8 is 20. Then 20 divided by 4, we have 5. Okay, and then from there, we're doing deviations. X minus 5, 8 minus 5. So we have negative 3, negative 1, 1, and 3. Okay, so if we added all these up, we get 0, right? So it's important for us to square all of those. So we go to square it. Negative 3 squared is 9. Negative 1 squared is 1. 1 squared is 1. And then 3 squared is 9. Okay. Then from there we add all of these up. So 9 plus 1 plus 1 plus 9 will give us 20. And that's our sum of squares. And we take 20 and we're going to divide it by 3. 20 divided by 3 will give us 6.67. And then if we take the square root of 6.67, for our standard deviation, we get 2.58. Okay, so let's take the standard deviation and this mean that we just calculated and apply it to this normal curve. So what I'm going to do at this point is draw a normal curve down here so that you can see it. Mean, median, mode. And the mean is in the middle, right? So we know that the sample mean for this particular data set is 5, right? Then we have plus 1 standard deviation, plus 2 standard deviation, plus 3. And then on this side are negative standard deviations, right? Okay, so we know hold on just a second. So we know that our mean in the center is 5, right? And if we go plus 1 standard deviation above the mean, that means we're taking our standard deviation of 2.58 and we're adding it on to that mean, okay? So again, the percentages up here don't really change. But what the standard deviations represented at the bottom is going to change based on what the data set is. And in particular, with this data set, this is what it would look like. So plus 1 standard deviation above 5 would give us a numeric of 7.58. And all we did was add 2.58 to 5. And then we add 2.58 again to 7.58, and that will give us 2 standard deviations above the mean. And then we do that again if we want to get 3 standard deviations above the mean in terms of this data set. Okay? So we wanted to look at the z-score for 4. Okay, so we wanted to transform it into a standard deviation, which is going to equate to this. Okay, so this is the raw score equivalent, but we want to transform it into a standard deviation so that we can see in regard to this particular sample where that 4 actually falls. Okay, so let's go ahead and calculate a z. So x would be the equivalent of 4 because that's the one that we're looking to solve. And then our sample mean is going to be 5 over 2.58. Right? So we got 4, sample mean is 5, standard deviation is 2.58 because that's what we calculated right here based on our steps to calculate the standard deviation. So we got 4 minus 5, which gives us a negative 1 over 2.58, which will give us negative 0.39. Okay, so again, we're taking the raw score 4 and we're transforming it into a standard deviation unit, and we got a negative 0.39. So the negative and the positive symbol tells us where that standard deviation is going to fall. If it's negative, it's going to fall on this end. If it's positive, it's going to fall on this end. So we got negative 0.39, which means that it likely falls probably right there in our data set, because what we did was we took a raw score, transformed it into a standard deviation. So because we did that, now we can apply it to this distribution, okay, and find out in terms of the rest of this data set how this score of 4 fared, okay. So with this, we can go to the back of our textbooks and look in our Z-table and find out the exact proportion of scores that fall at 4 and below. Okay, and as you can see, it's about 50%. Now, some of you guys may be going, okay, if it was exactly 50% of scores that fall at 4 and below, then why isn't negative 0.39 0? In other words, why isn't it coming in the middle? Well, this normal curve, although these percentages are very much fixed, it really applies to scores that are of a large sample size. Here we got a pretty small sample size, so it's going to be a little bit off, but for the most part, it still gives us an idea of how 4 fared in regard to this sample's particular mean as well as the rest of the distribution. Okay, so let's wrap things up. Just to recap, a normal curve is a bell-shaped curve, represents normal distribution, it's symmetrical, the whole distribution equates to 50%, with 50% on the right side, 50% on the left side. Positive scores on the right side, negative scores on the left side. These percentages are fixed. Everything under here is going to change based on the data set, and we're talking about this distribution here because it's going to give us a lot of information as it pertains to samples and specific raw scores as it relates to measures of central tendency as well as measures of variance or standard deviations. I hope this helped. I know it was a bit long. Let me know what you think.